Hello everyone and welcome this afternoon to our next session of our Digital V-Days. And yeah, I'm very happy to welcome all of you to our topic today, the novel topologies and wide bandgap combine for a compact and efficient 1 kilowatt power supply. I'm happy to also introduce our speaker today, Alessandro Maggioni. And yeah, he is from onsemi, and I'm very happy to welcome him today as well. You will, so he will do the presentation and answer all your questions at the end of the presentation. And yeah, you can just easily send us your questions within the chat. And then also later on, we will share as well the handout and the recording with you. So that's enough from my side. I wish you an exciting webinar and yeah, have fun.
Good afternoon, everybody. So thanks to, first of all, to Würth Elektronik's team for the opportunity and welcome to this session of Digital Days. My name is Alessandro Maggioni and I'm responsible as a regional marketing manager for the EMEA region for the analog and mixed signal group inside onsemi. So in this presentation, we will try to highlight how to design with a bridgeless totem pole power factor corrector a compact and efficient 1 kilowatt power supply. So let's have a look. So here is the agenda for today. So we will take a look about the AC/DC power supply landscape. So then we will talk about PFC or power factor corrector. So why it's needed. The solution can be implemented and the control techniques, especially on CRM or critical conduction mode. Higher efficiency, so why there is a growing demand of energy efficiency solution. So we will go to have a comparison between bridge versus bridgeless totem pole and which perform better. Then we will have a look on our solution for bridgeless totem pole PFC controller, so the onsemi NCP1681, so based on a multi-mode or CCM control mode. We will spend also some time, some slide introducing our reference board based on NCP1681, so and relative additional key parts, so able to achieve 1 kilowatt with very high efficiency, and then at the end, some time available for any question and relative answer. So let's start. First of all, ICT power supply are extensively used in several vertical markets, including industrial, automotive, medical, smart cities, clouds, and so on. So more recently, the growing adoption of the wide bandgap devices, such as gallium nitride, so GaN, or silicon carbide, SiC, has directly impacted the expansion of ADCC power supplies in the market. So over the past years, owing the advancement in technology, so GaN and SiC technologies has increasingly become more feasible for commercial application. AC/DC power supplies are still the major power supplies product type in the market, so let's accounting more than 65% of the market revenue, so back in 2021, and around up to 80% in 2030, so this is a forecast, so with the DC/DC converter accounting for the rest. This is driving the manufacturer. So as a demand for all these products and the above market segment is increasing, so the production of the AC/DC power supply is also rising. At the back of this factor, along with the focus of revamping the electronic sectors, the global power supply adapter market is expected to attain a market value of around $50 billion by end of 2030, and is expected to grow as a compound annual growth rate of around 5%. So in Europe, so they call it the Euro 5, so like Germany, UK, France, Italy, and Spain, all the biggest share of Euro power supply market. So owing the strong growth of industrial electronics, industrial and automotive sectors in these countries. PFC, why? So AC power has two components. So the real power or active power, so sometimes also called the average power, which is expressed in watts. We have also the reactive power, so usually expressed in reactive volt ampere, so OVAR. As power is transferred along a transmission line, it does not consist purely of a real power, so that can do the work once transferred to the load, but rather consists of a combination of a real and reactive power, so what is called apparent power. So the power factor of an AC power system is defined as the ratio of the real power absorbed by the load to the apparent power flow into the circuit. A power factor of less than 1 indicates the voltage and the current and the input are not in phase. So this means reducing the average product of the two. So the current waveform here does not follow the voltage waveform. So voltage and current here are more or less in phase. So great. So this means that we have a good power factor. So wrong. So the measured power factor here is around 0.6. So this results not only in a power losses, but also may causes harmonics distraction that travel down the neutral line and disrupt other devices connected to the line. So here you can see in the same condition, but adding a PFC stage up front, that the current and the voltage waveform are very close to each other. So with a very improved THD reducing all the harmonics components and harmonics distortion. PFC solution. So how to move from left to right? So which is the solution? You need to shape the inductor current in order to match the input voltage waveform. So how? So we said before, inserting a switch mode boost converter stage between rectifier and the bulk storage cap. So now a simple example of why converter stage between the rectifier and the bulk storage cap is improving to have a very good power factor in your C power line. Here you have two glasses of beer, so both are objectively full, and you will pay in both cases as full glasses. So, but on the left side you have a very poor power factor, so around 0.6, while on the right side you have a very good power factor, so well above 0.9. So, and the thing is, everyone prefers to have the right one. Okay. High demand of energy efficiency solution. As we discussed over the past decades, environment concern across an array of industrial domain had forced the player in the global AC/DC power supply adapter market to lean toward the development of energy efficiency components. Most of the world electrical engineering is supplied by AC/DC power supplies, so as we saw in the first slides, and they are found in almost all mains power equipment and devices. So meaning that their efficiency has a huge impact on the operating cost as well, contributing significantly to emission. The input bridge rectifier found in almost AC/DC power supplies contribute losses that present a real challenge in achieving the highest possible efficiency figures. So however, removing the traditional diode bridge, so PFC FET, boost diode, so in a favor of a bridgeless totem pole PFC arrangement, enhance the efficiency through the use of active switches. Okay. Most commonly, PFC use a boost converter to drive on a high DC level, higher than the mains voltage peak, so from the rectifier mains. This level is DC level is typically 395 or 400 volts, so a power supply designed for universal input, so 90 to 264 volt AC input. Is then regulated using an isolated DC-DC conversion stage to produce the required DC output voltage for the power supply unit. So a valuable byproduct of this is that the line current flows the line voltage waveform, giving, in theory at least, so the unit power factor. To approach above is effective, and the PFC can be designed to operate in continuous disconduction or critical conduction mode, so we'll call CCM, DCM, or CRM, so which are largely defined by whatever energy in the boosting inductor fully exhausts during each time or not. Normally, there is a loss of 2% within the DC-DC stage and around 1% in the line rectification and PF stage, sometimes even higher. So although this is much closer to 2% during operation and real low line. So which close to 4% losses at the low line, there is a significant challenge, for example, in meeting the strictly 80 plus titanium standard level. So that required to have an efficiency up to 96% at the 230 volt input at 50% load. So this is a specification commonly used in server. How to make boost PFC more efficient? So always remember the golden rule. So a better efficiency with fewer devices in the conduction path. So on the right side, you have the typical PFC with bridge diodes and so on. On the left side, you have the bridges totem pole PFC. So the topology consists of two half bridges configuration. So one half bridge, commonly referred as a fast leg, switches at the PWM frequency of the controller. So, and the other, so is commonly referred as the slow leg, switches at the AC line frequency. The fast leg performs the role of the switch and the diode in a classical boost PFC. So that is this switches function to regulate the output voltage and shape the input current to provide the high power factor and low harmonic distortion. The slow leg switches perform the role of the diode bridge in a classical boost PFC. Active switch with a very low on resistance are utilized instead of diode, in resulting to improve the efficiency. The totem pole PFC operate with only one slow leg and one fast leg device in the conduction path, whereas the conventional boost PFC operate with two bridges diodes and one active switch or boost diode in the conduction path. So fewer devices in the conduction path and active switches replacing the bridge diode then allow the totem pole PFC topology to achieve a higher system efficiency and low power and high power density than the classical boost PFC. Totem pole PFC is a derivative of a standard boost PFC converter, so where the bridge diodes are removed and therefore the boost circuitry directly interface with the AC input. So the key challenge with this approach are the detection of the line polarity, so the current sense and the current limit implementation. Further, the totem pole PFC is a synchronous boost, so converter, as opposed as a standard boost PFC implementation. So therefore, a zero current detection scheme needs to be implemented, as you see as an unrectified AC line. All the above mentioned requirements are implemented, of course, in the NCP1681. It is also important to note that the similarities are to a standard boost PFC. So the criteria for selecting the boost inductors, the output capacitor, the boost FET are exactly the same between a totem pole PFC and a standard boost PFC. So in this slide we can see real difference, real measurements from a totem pole versus a standard boost efficiency comparison. So this is a 500 watt multi-board PFC. So we have the totem pole with the orange line and the standard boost with red lines. So for the totem pole we are using two GANs and two superjunction FET. So two GANs for the fast leg and two superjunction for the slow leg, while the standard boost uses two superjunction FET and one silicon carbide diode. So we can see here that the maximum power, so the efficiency is around 1.8% in gain. So this means a 30% reduction in losses, and at 500 watt with a 90 volt AC input condition, so the worst case, it's equivalent to 9 watt power loss reduction. So let's now have a look about the NCP1681, so our bridgeless totem pole CCM PFC controller. We have here we have a table which is showing the topology overview of the power factor correction. So we have the interleave boost, the semi-bridges boost, interleave CRM totem pole, and the bridges totem pole. So which are the advantages of the bridges totem pole compared to the other solution? First of all, we have the transistor. So the bridges totem pole can use a silicon superjunction FET, GAN or SiC for critical conduction mode, while only one bang up devices we suggest for critical conduction mode, so for switching. Switching frequency, let's say for CRM, it can be up to 500 kHz, but even up to 1 MHz is possible. The advantage are, of course, higher efficiency, so zero QRR for when using GAN, highest power density, and low components count. And the cost, considering the performance, are slightly higher than a standard boost converter. which are the application in which you can use a bridge totem pole PLC. So basically, can be data center, rack-mounted power supplies, high-power LED street lights, industrial power supplies, 5G telecom power supplies, and so on. So external adapter. So basically, where all the application where efficiency and compactness are a real critical parameter. So, which is the totem pole scenario today? So, totem pole is not a brand new topology, so it's well used since a while, but on the market today, the only existing solution are MCU based. So, what does means? Means, of course, high BOM cost, a software code development, so means to perform and to define a proper software code, and of course, a more complex design and time consuming. We, as onsemi, we are bringing with the NCP1681 and 80, so which is a pure mixed signal devices family. We are bringing, of course, cost effective, so is not based on MCU, so the costs are much lower. The devices are designed for having optimal bill of material, and of course this means a fast development timing, so really fast time to market. Here we have some introduction about our device. So here we talk about 1681. So this is a multi-mode or CCM controller. He's capable of operating on fixed frequency in CCM or in a constant on time, and he has a value synchronized frequency fallback, so to optimize efficiency across the entire load range. It comes with a novel current sense scheme, so which is providing the inductor current upslope and downslope sensing. So this will reduce in a cycle by cycle current limit without the use of Hall effect sensor, which are more expensive. It includes all the linear polarity detection, so digital loop compensation, so which allow to reduce the external components, and the fact that he has a frequency, fixed frequency CCM, constant on time, CRM, and value switch frequency fallback is allowed to optimize the performance really across all the power level. We have today 3 devices released, so the 61A and AA and AB, so which are both CCM operation mode, and the difference is the switching frequency. So one is clamped at 65 kilohertz, with the other one, so the AB, is working at 95 kilohertz. And then we have the NCP1681 BA, which is a multi-mode version, so which is moving from multi-mode in medium load to CCM, CRM mode in light loads to CCM in heavy loads, which has a frequency of 65 kilohertz in CCM. Here, if we make a comparison between totem pole PLC mixed signal versus digital controller, so which are the comparison between the two. So first of all, for a digital controller, to the fact that he has a MCU, you need a complex design, more complex design to perform a software dedicated. Of course, here you're addressing more high-end server, high-end power supplies or clouds. While the NCP the 68 family, so he can come with 3 devices, 6080, which is in CRM, so which is performing adapt to all the power supplies up to, say, around 350 watt. We have the 6081 in multi-mode, which is suitable for all the application between 350 watt up to, let's say, 1 kilowatt. And then we have the 6081 in CCM only mode, which is addressing all the application up to around 3-4 kilowatt. In terms of flexibility, of course, the digital controller can support multi-topologies, so boost, PFC, totem pole PFC, voltage mode LLC, and so on. So this is really depending on the software you're going to run, while the device, the 6081, is optimized for totem pole PFC, CRM, and CCM. So this means that no additional components around, but what is really needed for the specific application. Flexibility. Of course, you can implement custom IPs for distinguish for competition, while our design is designed to pass the standards for power supplies. So it's designed for do that. For what regards the standby power, so digital controller of course has a limited poor standby power, so you need always an ACC for running the DSP or the MCU, so which is a high consumption, while the device, since the fact that it doesn't have an MCU or a DSP, has an excellent light load efficiency and standby power. THD, of course, with digital controller you go down to less than 2%. You can work with lookup tables and custom IPs, while with the 6080 with CRM, so the THD is better than all the standards, and with the 6081 the THD is lower than the 5%, so enough to supply most of the industrial application for power supplies. Telemetry, of course, this can be implemented with a digital controller, so via PM bus, while we have no telemetry in the PFC. So those means that those devices are really applicable for even for lower power and lower cost solution than high-end application. So let's then talk about the reference design. So we have with this 1 kilowatt in universal input, so 50 volt output power supply. What we are talking about, so here you can see the pictures. The picture is basically on the high hand of the slide. You can see the top. So basically you can see the inductor. Here you have on the bottom side you have the PFC choke. Then on the higher side you have LLC. So the board of course is composed by a totem pole PFC plus LLC stage. On the bottom you see the components. So with the LLC, with the controller, the silicon, the MOSFET for the rectification, while here on the bottom of the high part you can see the control board for the controller. So it's based on a totem pole PFC controller with NCP1681 and also with our onsemi LCC controller, so NCL30159. So which they use for a very high power factor and very low THD performance. Means that he has a very high efficiency thanks to the 6081. We are using here integrating driver, so our NCP1681 we've integrated the GAN with integrated driver. The device comes with all the protection like over voltage protection, over current protection, so also constant power protection is done by the NCL30159 and the NCL30159 and the device, the reference comes with a very high power factor and very low THD. Which are the performance of this board? So we can see here input voltage from 90 volt AC to 260 volt AC. Output voltage is fixed, 50 volt. Output current is 20 amps, so we can have up to 115 amps up to 150 volt AC without using a fan cooling. With fan cooling you can go up to 20 amps as well. Power factor more than 94% with 20% of load, and close to 0.998 with 100% load with full input range. The size, so this is the most important point, because here we really achieve a very high density, which is basically impossible to do with existing solution on the market. The size is only 22 centimeters by 8.5 centimeters by 5 centimeter thick. Average efficiency of the system, 94.6% with low line, so 115 volt AC, 96.1% with high line, so 230 volt AC, reaching a peak of 95.4 for 150 volt AC and 96.5% peak for 230 volt AC. The construction also is important, so we are not using a strange material, but it's a standard 4-layer FR4 PCB with 2 layers for the board for LLC and the PFC controller. Here we can see the schematic or the block diagrams. So on the left side we have the totem pole PFC controller 6081, so which is controlling the NCP51530, so which is a high voltage driver, half bridge, which is driving the slow leg driver. And here we have, as a slow leg, we are using two super junction FET, so F07 and 65. Then we have the PFC controller, which is driving the NCP1681 so which is a little isolated dual channel half bridge gate driver. So using for the fast leg, which is driving two times integrated driver gun, so 50 milliohm, so the NCP58921. Then we have the half bridge stages for the LCS controller, which is driving for MOSFET for the synchronous rectification, and then we have two times the NCP4306, which is a synchronous rectification controller for the secondary side, and then we also have the NCL30159 which is a feedback loop controller to keep the control loop for the LLC. In this slide, we can see listed basically the key components of this reference design. So talking from the PFC controller with the NCP1681, so the LLC controller, we already talked about the NCL30159, the synchronous rectification controller, the 4306. For the gate drivers, we are using for the fast leg, the isolated driver NCP51561, for the slow leg, the 51530. And if we're talking about the switching devices, so for the fast leg, we are using the integrated driver gun NCP58921, while for the slow leg, we're using a standard super junction FET. So we talked already about the NCP1681, so let's have a quick look also on the other key components. Here we have the NCL30159, so which is an LLC half bridge controller. So is a primary side current mode LLC controller. So the device controller can also provide wide dimming range in case of LED operation in wide output condition. So the controller also allows to have implemented many features like high efficiency standby, dedicated startup, and allows to ensure the maximum power limit feature. It also enables to design the wide input voltage range converters, or in case of LED drivers, with the output match the different LED strings. So this means that it currently is a built-in 700 volt 0.8 amps driver. It has this 700 volt high voltage startup. It comes with advanced light load mode, so that to have a very low standby power. And also is suitable for industrial power supplies, dimmable high perform dimmable LED driver, and so on. We also have the NCL30486B, which is a CC/CCV PSR controller. Is an IPF single stage constant current and constant voltage PSR PWM controller. Suitable for flyback, buck boost, SAPIC, and boost, so very flexible. It's also integrated a 700 volt high voltage startup, very precise current regulation, very precise voltage regulation, works for very high level power factor, so more than 0.95, and very high implementation of THD, so less than 10%. It works in a quasi-resonant control, standby mode, can comes with different, for example, flavor for dimming features in case of using of LED driver application, and this is very compact, also including all the kind of protection for correct power supply application. For the secondary side, we have the NCP4306, so is a secondary side synchronous rectification driver. Is a very high performance driver, so this is there to control a synchronous rectification MOSFET in all this kind of switch mode power supply. So thanks to high performance driver and also the versatility, it can be used to vary several topologies, so PCM, CCM, flyback, quasi-resonant flyback, half resonant bridge, and so on. It can work, as we say, in different modes, so CCM, DCM, quasi-resonant, flyback, LC, and so on. It has a very, very short turn-off delay, less than 15 nanoseconds. It has an adjustable minimum on and off time. very high DV detection, very high power driver capability. So we talk about 7 amp sink and 2 amp in source drive. And this is a device which is already tailored for driving GaN transistor, so for very high performance. If we're talking about the integrated driver GaN, so we are introducing our new family of NCP1681 X family. So it's a 650 volt integrated GaN in a PQFN package. So it's a driver GaN with built-in 6 volt clamped gate driver for optimal and robust GaN operation at very high switching frequency. So the device is coming with a very low inductance PQFN bottom cool package. So the family is composed by integrated driver plus an enhanced mode GaN transistor. So it comes with 3 different RDS-on, 50, 78, and 150 million. That's a typical RDS-on. We say that it's a 650 volt breakdown voltage driver, 6 volt internal clamp GaN to preserve the gate driver of the GaN. The maximum driver VCC is up to 20 volt, and it comes with only 35 nanosecond typical driver propagation delay time. The device, as we mentioned, is 8 by 8 millimeter standard PQFN in a bottom side cooling. So this is a perfect solution for totem pole PFC and LLC for fast leg or high performance half bridge LLC application. For what regards the slow leg, we are using the NCP51530, which is a very high performance 700 volt half bridge driver. It's a high frequency, high side and low side driver, so with very low and matched propagation delay time. So in order that you can drive directly 2N channel power MOSFET for very high performance SMPS and power converter. So 100 nanosecond maximum propagation delay time, only 5 nanosecond of delay of matching, 50 nanosecond rise and fall times, and the device is able to sustain a negative bridge voltage down to minus 10 volt. We have quite good performance source and sink current capability, so 3.5 amps source and 3 amps as a sink, and the under voltage lockout for both inputs. It also comes in 2 different packages, so standard SO8 or for space constraint application, a DFN 10 leads 4x4 millimeter. Using the NCP51561, so 5 kilovolt isolated high-speed dual driver, is an isolated dual channel driver with up to 4.5 and 9 amps source and sink peak current capability. Offers a very short and matched propagation delay times, so only 36 nanosecond and 8 nanosecond of delayed matching. It provides a very high DV on DT immunity, so the device is able on average to sustain more than 200 volt per nanosecond. The device comes with different programmable input logic, so it can go with a single or dual input modes via the A and B pin. It comes with disable or enables mode. The device also has a user programmable dead time control, and the device comes with different under voltage lockout options. So 8 volt, 17 volt. We can also have some devices on demand with like 5 or 13 volt. So this is in order to match the best under voltage lockout threshold, for example, if you're using a MOSFET or a silicon carbide driver. Now let's have a look of the board stages. Here we have the schematic control of the PFC board control. So here we have the NCP1681, so highlighted here, so which is a fixed frequency continuous conductor mode designed for totem pole PFC. So the device has AC line monitoring circuitry and AC phase detection. It works in multi-mode operation or a standard CCM. He has the brownout detection, frequency fallback, skip mode, and power factor corrector OK indicator, so which is providing a signal to the LLC when the output voltage of the PFC reach the proper level. And then here you can see how the control board is implemented. So basically you have all the components on one side, so very minimal component accounts. For what regarding the PFC fast leg switchboard, so here we have the two integrated driver GAN, so NCP1681, so which is a fast leg stage, half bridge, so it's based on 50 milliohm NCP 5891, so up to 30 amp GAN with integrated driver. So this is the, and here is the Gerber, which is show the dimension of the board. For what regarding the main board parts, here we can see the schematic. So here I highlighted the two power MOSFETs, super junction FET, so 650 volt, 44 amps, only 77 milliohm, housing in a package like TO220F. Here we have highlighted the driver, so the NCP51530. So we again is a 700 volt high frequency, high side and low side driver, so with a very low and matched propagation delay times. And here we have the NCP51561, which is an isolated dual channel gate driver with high performance source and seek current capability. And here you can see the main board, so the top side and the bottom side. So you can see really how low components count can be attached here. If we're talking about the LLC part, so here is the main schematic. Here you can see the LLC controller, so the NCL30159. So again, is a primary side current mode LLC controller. So this controller can provide a wide dimming range in wide output operation condition and very good THD performance. We have twice the NCP4306 high performance driver, which is there for control a synchronous rectification MOSFET in power supplies. And then we have the NCL30486, which is a high power factor single stage constant current, constant voltage, with PSR, PWM controller. So we're very flexible, we can address different topologies like buck boost, SAPIC, flyback, and so on. Now, when we look at which kind of evaluation result we have, so then we can see in the next slides. So here we can see the efficiency versus the output power. So as we discussed, we show in the previous slide, so here we can see the average curve. So we start with very good behaviors already from low light loads. So for 1 amps, we're already above 85-86%. So which is reaching the peak of the efficiency around 7 amp with 95.4% with the low line and up to 96.5%, reached around 13 amps in the high line. And the device has the reference design has average efficiency of 96.1%. We are talking about 240 volt AC input, or 94.6% when we're talking about 150 volt AC. Power factor versus output power. Also here is an important point to take into account. And then you can see that already when we have more than 30% of loads, so the power factor is always close to 1. So we're reaching the peak in this area. So very close to the 1 value, the unit value. Total harmonic destruction. THD, so this is a multi-mode device, so it works here when it was in CRM mode and then here when it's a transition. So you can see that in this area, so the THD are much lower than the 5%. So we are, let's say, below 5% in all cases, let's say already higher than 5.5 amps of load. And here you can see some waveforms. So here you can see the behavior at the startups. So we have in orange, in yellow we have the startup sequencing. So we have in light blue we have the low side of the fast leg, the low side of the fast leg, the drivers, so the VCC, the PFC output voltage, and in purple you see the current into the choke. And you can see in different conditions, input with 150 volt AC and 230 volt AC. So here's the overall startup, and you can see a little bit in more in details the screen of the input side. The transition from DCM to CCM, so this is also important to see. So you can see here in this area when in transition, so the transition happens around 1.7 amp in low line, and happens around 4.3 amps when we are using a 230 volt AC input. And you can see here in the detail how smooth the transition is. When we are talking about full loads, here we have the screenshot as well. So you can see again the behavior with low line at 1 amp, full load 230 volt and 1 amp of load. And here we can see the LLC waveform, so the controller. So you can see here how is the behavior during the startup. So you can see the behavior when the device is in the skip mode, so with around 0.2 amps of load. When the device moves to a light load, so when we have around 1 amps, and then when we are half load, so in the range of 10 amps. So you can see how the behavior of LLC is in this area. Full load, so also here the behavior, not spend too much time. And then you can see also quite important the output ripple. So full load, 20 amps, half load, and in very light load mode with 100 milliamps, which is the device is running in skip mode. When we are coming to the highlights, what we can see about this reference design. So first of all, high efficiency performance. So we see the fact that using very high performance LLC, high performance totem pole PFC, integrated driver gun. So the overall high efficiency is very, very high. The device provide the reference design provide a high level of protection, like overcurrent protection, overvoltage protection, and short circuit protection. The reference design is also tailored to work in an open loop protection. And of course, this reference design also works with a constant current, constant voltage mode, so with a very deep skip mode. We are now at the end of this presentation, so thanks for the timing today. Thanks for joining us. So if you have any question, feel free to ask. And if you need more information, please go to visit our website onsemi.com. Thanks a lot.
Yeah, so thank you, Alessandro, for your presentation. And yeah, I would say I will quickly share as well with you the handout, so you will have access to that and can directly download it. Also, we will share the link with you later on. And then I would say we would jump right into your questions, because we saw there were a lot of questions coming in. Time-wise, probably we can't answer all questions now in the live webinar, but then Alessandro will answer them later on via email. So Alessandro, thank you. I see you're with me. So then let's start into the chat or into the questions. And first question is, which is the maximum switching frequency achievable by a CCM bridgeless totem pole?
It's a good question. So let's say that using wide bandgap devices, a reasonable frequency or maximum frequency you can achieve reasonable is 350 kilohertz, but in theory can be even much higher, so almost even double. So depends, of course, on the power level.
Okay, thank you very much. Then next question. Could the conducting losses be reduced by using a lower RD-SON ST MOSFET for the low frequency switching lag? So wasn't it implemented?
In principle, yes. So, of course, as we've seen at the beginning, reducing the resistive path, of course, it can help. It's always a matter of compromise between cost and performance. So we saw that in this case, a 67 million super junction was be more than enough have a reasonable, quite good performance. So going lower is affecting, yes, but not enough to compensate the cost.
Okay, thank you very much. So then next question, and this question is referred to page 25, page 25. Why you used GAN and not SiC?
Okay, so as mentioned in the presentation, so using wide bandgap is a must or strongly recommended for totem pole PFC. In this particular case, we're using GAN because it's up to 1 kilowatt, and using GAN in this case will help to keep the solution more compact, reducing the size even compared to SiC, even reducing the size of the heat sink for the fast leg. So this is main reason. For we also have, of course, application with higher power, like 2-3 kilowatt, in which that case using the SiC FET it's mandatory, I would say.
Okay, Alessandro, thank you very much for that answer. Then let's go on with the next question. Why is wide bandgap semiconductor needed for totem pole PFC?
Yeah, so we saw before, especially in the CCN, totem pole PFC is a hard switching topology. If you take about, for example, GAN, so he has no inherent voltage diode, so there is no reverse cover charge. In that would contribute to the switching loss. So this means that enabling the ultimate PFC efficiency to be achieved. The body die of the SiC MOSFET still has no zero reverse recovery charge, but it's much lower compared to the standard silicon MOSFET. So this is why we expected that the efficiency of a totem pole PFC will be a little bit higher with GaN compared to the SiC, but much higher compared to the standard silicon.
Okay. Alessandro, thank you very much. Then I would say we will go into the last question, because the next session will come from our digital V-Days. So you see the question right now. In the case the supply voltage has substantial harmonics, does your controller regulate the current to the same shape or to a sine wave?
Okay, so this should be a little bit longer, but I try to minimize. So basically, the controller regulated to the current shape, so PFC close to 1, but we are implemented so what is called a THD enhancer. So which is a feature that basically it works in conjunction, for example, with the dead time compensation. So these allow to have a better performance of THD across the line and load. So, but for more information, I would suggest to go to the datasheet.
Okay, thank you very much. So then we are already at the end of this session of our digital V-Days. Thank you once again, Alessandro, for your time today.
Thanks a lot for your time. Thanks to everybody.
Yeah, then thank you for your attention, and I hope you stay tuned at our digital V-Days, and I wish you a good afternoon. Bye.
Thank you. Bye.